Hello everybody. Thank you all for coming to my talk about AWS Architecture and a practical guide. I hope to convey to you 3 key takeaways. How to manage complex projects like setting up a full AWS infrastructure, how to design an AWS architecture in 12 steps, and also to show you a demo on how to build your AWS architecture using Java. But let's first talk about my first steps. I just joined a startup coming out of university, and we sold a demo on a single VM to a customer. So now we had this need for highly available infrastructure. And being a startup, this whole responsibility came to me. And it was a great learning experience for me personally. And I was amazed about AWS coming from traditional hosting. But quickly, we were overwhelmed by AWS. There are so many choices to make. And there are so many things on how to solve problems. Like you can solve computation with EC2, containers, lambdas. At the infrastructure as code side, we picked Terraform, but we were unsure if we should add Terragrant. And then finally, to protect ourselves, should we only use security groups, or do we need network ACLs? So we felt sluggish. We had no moment of success. We were uncertain of ourselves, and business started to get anxious. We could not give certain timelines. So this feeling is common, and I see a lot of companies having the same experience. So you're not alone. A lot of engineers run into the problems of the complexity of AWS. And you can study for certifications, but that's just like studying at university. You lack the experience. And the information about AWS can be very unopinionated, especially from AWS documentation. It only says what you can do, not what you should do. Even if it tells you opinionated information, the direction can be outdated. So there's no optimal solution anymore. And I help companies with these mistakes. But even for me, it's hard sometimes. I did my certification as an AWS Solution Architect Pro, and I still felt sometimes out of my depth. So I need a systematic approach for myself. Because if we don't get this right, it's like moving mountains. Infrastructure migrations are very costly, because we have to move production workloads. This can involve data sync problems, downtime, and often the infrastructure capacity is not there when we have to do these big projects. So the solution is we need a systematic approach for these complex projects. The solution is to divide up the problem and solve them separately. And you can follow these 12 steps that I will show you. So I'm Steffan Norberhuis. I'm a freelance AWS and DevOps consultant. You can follow me on Twitter. The slides are also up there. And my email is easy to remember. So feel free to contact me. Let's look at why a systematic approach helps us. We have to set some design principles. And the first thing I always do coming into a project is setting the project goal. And this is really a business goal. What is the long-term objective of the project, and what is the short-term goal? Then I can architect appropriately. I need to understand the cloud strategy of the company. Why are they moving to the cloud? Why are they moving to AWS? Because if we can answer these questions, then we know if we can allow AWS vendor lock-in. AWS provides great resources that allow you to go to market quickly, but this comes at the cost of AWS lock-in. You should strive to adopt a single cloud. If you're open to move away from AWS in the future, you will only be able to select the common denominator amongst clouds, and you cannot pick the best solutions that AWS offers. And it's also important to understand that AWS is no magic bullet. AWS takes work. AWS takes investment in technology, but also in people. So when I get a project, I define a project type. Is it either a greenfield project where everything is easy? We start from scratch. Are we going to repurchase? You're going to look into the market and buy the service instead of rehosting. Which is the next thing. Rehosting is to quickly lift and shift into AWS, but this often comes at a high operational cost. Then we can re-platform. We had some smart choices on how to optimize the current workload for AWS. And finally, we can refactor, where we rebuild the complete project in AWS natively. So now we have clear what the goal of the project is and how we're going to tackle it. We now need to deal with the complexity of AWS. And how do we deal with the complexity? There are several techniques for this. And there are three concepts that are important: incremental, iteratively, and divide and conquer. And I combine those three, and let's look at that. So the first is incremental. If we're going to paint the Mona Lisa, incremental is we're first going to paint the top half. We've fully completed and we finish it. Then we go to the next part, the left bottom, and finally we finish the full Mona Lisa. But this is of course unrealistic to get this level of detail. So often we do iteratively, where we make a sketch of the Mona Lisa, we fill in some colors and focus on important details, and then finally we know what we want and we finish it. But we can also combine these two approaches. So we do an incremental, iteratively approach. We add detail where it matters. We want to get the head right, so we add more detail there. In the next steps, we want to add even more detail, but we also see that we need to get the hands right. And then only then, we finish the whole painting. And this is also what I do in AWS Architecture. First, we need to know where are we now? Is there a current design? Then we can create the next step and also a target design, something that we would strive for. But we will only be building for the next increment, the next step design. Now, the third concept is divide and conquer. With AWS, you can divide it in three big parts. It's the platform, where you host your workloads, the service itself, and how you're going to maintain it. So, if you have to design a full AWS infrastructure, you can use this approach. First, you have to set up the account structure. Then we set up access, roles, and permissions. We pick the regions and the points of residence that we're going to host in. Then we build a VPC and networking to host our workloads. Then we move to the service side, and we select the endpoints that our customers are going to connect to. Pick how we're going to store our customer data, decide upon how we're going to do computations on the data, and after we have processed some business flows, we want to notify people with events. Now, this design needs to be deployed to the cloud with CI/CD. Then we need to operate it, and finally, we want to do everything securely and at a minimal cost. So this is how we're going to tackle the complexity. But also, let's look at how we're going to use the timelines. And we can learn a lot from John F. Kennedy, that was at the head of the most complex project ever implemented by man. He said, "I believe that this nation should commit itself to achieving the goal before this decade is out, of landing a man on the moon and returning him safely to the Earth." This was said when we didn't even go into space. And the project leads at NASA used this goal to plan backwards. They planned Apollo missions to build the technology to land on the moon. They used the Gemini missions to build the technology to get to the moon. And finally, they used the Mercury missions to get into orbit. This was all planned years in advance. And we can use the same technique to plan backwards. Because why do I emphasize timelines? Because infrastructure projects can run very late. And they do not use realistic timelines. And if you're not keen on this, there are three driving factors that will get you to run late. First is that we will always strive for more accuracy. You can always continue to improve your design, and there's always more to research. So this is a driving factor that makes us run late. Secondly, we take up the time that's allowed for it. If you say this is going to take 3 months, it will take 3 months. And of course, there's always a factor of student procrastination. Even highly paid engineers are more productive when a timeline date comes up. So that's why I introduced these timelines in these infrastructure projects. And of course, we are not slaves, so we can always ask for more time. So if you have the 12 steps, you can plot them on a timeline. They don't take the same amount of time, but you can use it to plan your execution. Every step can be an epic of work, where you can design and finish it. Now you can start planning. If anything comes up during a phase, but it fits another epic later on, you can just add there and keep focus. So I can plan this for July, well, there's a mistake here, but for 3 months, finish in August. But I can also say it takes 3 weeks. And it's also handy to visualize complexity. Also on time. So if you have the project time, we can divide it. And at first, we will deal with a lot of uncertainty. Then, things will get more certain. And this is a hill that we have to climb, called the hill chart. First, we'll be figuring things out. We'll do a lot of design. But when we reach the crest of the hill, we'll start implementing more and more. And once we are over the apex, we will start to implement more and design less. So we're making it happen. And now you can visualize where your project is. First, you will start implementing some stuff, but mostly designing. After that, design is mostly complete. You start implementing, and you can start finishing up. Then we'll implement more and more, and only a certain little bit of uncertainty is left before we finish. This allows us to communicate. For example, if I have the AWS infrastructure project, I can plot this and show this to key stakeholders. Accounts in IAM is almost done. We're still figuring some things out for regions. For VPC, we're just starting, and we have no idea what we're going to do for endpoints. The key takeaway is, failing to plan is planning to fail. Now we need to know who's going to build AWS infrastructure. We need to ensure that we have the right skill set to do so. I often help small companies that call in my help too late. If they would ask me sooner, I can save a lot of time in future migrations. So who will build AWS? I see some common examples. The first is a single ops engineer for the whole company. He builds all infrastructure and then he leaves. Now the company has to rebuild everything, so don't do this. Then there's a single ops team. They build all the infrastructure, but they become the bottleneck. They become flooded with requests, and there's no time for innovation. A more mature approach is to have one ops engineer per team. But you still have the problem of just having one person. He will leave, and the team now has to rebuild everything. For smaller size companies, you want to have a DevOps team. Here, everybody contributes to the infrastructure's code, so everyone can build it. But there could be a specialist that takes the lead in this. Then for very large companies, you introduce a platform team with multiple DevOps teams. The platform team builds a platform for AWS, and the DevOps teams just configures it. So this is really how to deal with AWS. Now I'm going to show you in 12 steps how to build it. The first step is to create AWS accounts. Let me tell you a story of why accounts are important. A colleague of mine was picking up a very minor task. He was going to resize the database on acceptance after performance testing. He pushed the button, and immediately I heard his phone go with an alarm. And he said, uh-oh, that's never good. So what he did is he actually resized the production database. So now the database was downscaling, and we had to wait for that to complete before we can scale it up again. In the post-mortem, we proposed to introduce an account per environment. Because accounts help us to decompose our AWS architecture. The same way as we decompose our software architecture, we want to divide our infrastructure in several problems domains. There are several benefits for this. The account gives us more bulkheads in different dimensions. It isolates problems within a single domain. This creates blast zones between problems. It reduces complexity overall. In a single account, you only need to think about a single problem domain. You can solve your problems with security, billing, scaling easily. And it also makes naming easy. So let's look at an example. For example, we first built a root account. We don't really do much in there. We built an organization with multiple teams. There we add more accounts for their workloads. And we divide environments. So every team has multiple accounts. Now we need to give access to people. This should be secure. A company I helped with almost stopped their cloud migration entirely. This was before I came onto the project. Because the first account got hacked and ran up a bill of 10,000 euros in the first week. So we need to give access to people securely. And we need to provide engineers, machines, and user access to the resources. There are several principles to this. Temporary credentials, strong identity management, and least privileged design. In AWS, we want to use the amazingly strong and useful IAM system for all machine identity access. Everything that's spun up in AWS gets an IAM role and policy. We can use this for fine-grained access and to authenticate ourselves. We can also give users access using IAM. We can integrate with an identity provider, and this allows us to provide temporary roles and permissions in IAM. This can all be done seamlessly with AWS resources. So if I go back to the example, we had single sign-on for our engineers to log on to. Then we use IAM to allow other roles and permissions to give access to the workload accounts. This is a very simple example. The next question is, where should I deploy everything? When I started with AWS, we were deployed in Frankfurt. We thought this is the closest to the Netherlands and it doesn't really matter. But we really wanted to move to Lambda. The only problem was it was not yet released in Frankfurt. We didn't think there's much difference between regions, but there is. So you cannot just pick the region what is closest to you. There are distinct differences. So you have to look at the whole list of regions and filter it down. I will go through 4 design factors that you need to design for. The first is data residency, and this is obvious. If we host customer data for the EU, we need to host it in locally. The US also wants their data to be hosted in the US, so you pick the regions that are allowed by law. Secondly, latency. Latency dominates the customer experience. While you can reduce it using content delivery networks and the AWS global network, the region location will still be a huge factor. You should measure this latency between your customers and the region. Thirdly, cost. The regions actually differ in cost. Taxes on hardware is notoriously high in Brazil, and there's an abundance of power in Stockholm leading to lower cost. So the costs can differ. And finally, regions can have a different update speed. Often, US East 1 and EU West 1 get new stuff first. Then there are several bigger regions that will get the updates faster. If you want to be on the latest and greatest, you have to account for this. Next, we need to decide how to deal with failure. A local zone or an availability zone can fail. And we don't want to go down because of a single outage in a data center. So we design for this. But if a full region fails, we need to do a lot of engineering and deal with latency to overcome these failures. So we need to decide upon the cost of mitigating the failure. So if I zoom into the production account of one of the teams, I say we're going to host in EU Central 1. But I don't want to go down if a data center goes down. So I use 2 availability zones. So let's build a private virtual cloud that can host everything. A colleague of mine told this story where he inherited a VPC, a virtual private cloud. They were doing large-scale computing on weather models. this involves a lot of machines and a lot of IP addresses. And the subnets were not large enough to support this. So he had to do a costly migration to new side arrangers to allow for enough room. So my point is, you need to plan your VPC and networks to ensure that everything works out in the future. And the first step is planning your network. Side arrangers are spaces of IP that you can use in your subnet. And you need to make sure that there's enough room and reduce the chance of overlap. Finally, you can add logic to the subnets to identify purpose based on IP or side arrange. Traffic is not free in AWS, so we have to plan it. You pay across availability zones, egress out of regions, AWS services, and out to the internet. So you want to reduce the cost of network by planning your traffic. Stay within regions and use AWS integration endpoints to reduce cost. Finally, you can use a shared VPC. This allows you to centrally control your VPC. You can now share managed resources like NAT gateways in the internet gateways. You only need one instead of for every account. You can also do internet inspection or traffic inspection because you centralize all the traffic. So I go back again to the example. I had a VPC. I had public subnets to allow traffic to reach us. And I had private networks where only we can reach the internet. We now need to select how our customers are going to reach us. At one project I worked on, we had this requirement we could not lose a single HTTP post. We would always want to return except 200. And later we can retry if there's a bug, but we will not want to lose customer data. We used API Gateway, and this allowed us easily to integrate with a queue. So we could solve it easily. You can have multiple requirements on this endpoint. You can have a static IP, rate limiting, mutual TLS, or authentication. And you can use your endpoint to solve this for you. There are several options, but often this is either API Gateway or a load balancer. The easiest solution is to use an application load balancer. This routes your traffic to your endpoints, but it is a very sturdy solution that can do highlights. But you can do so much more with an API Gateway, and this is my preferred choice. You can do integration to any service, and it provides great visibility. Finally, in this step, you should also design the URLs that customer will use. You can incorporate their environment and regions to make URLs predictable in the future. This prevents costly migrations later on. So, going back to the example. I had Route 53 for my domain names. I had a load balancer in my public subnets where the customers can connect to. We can now have a look at how we're going to store data. Everything is a file in Linux, because how you store data is going to dictate how you're going to do operations on it. And the same holds true at AWS. One company cried for my help. After 2 years of developing, they could only scale up to 25 users because they stored the data wrongly in AWS. And we often both need OLTP and OLAP. OLTP stands for Online Transaction Processing. This is executing transactions in online banking, shopping, or order entry. The definition of a transaction has expanded greatly. Online analytic processing is aggregating these transactions into business intelligence. These are big and heavy queries that can run your production system into the ground. So you want to separate them. Often, databases are called relational or non-relational, but you can still store relational data in a non-relational database. So I prefer to call them SQL and NoSQL. SQL traditionally optimized for storage, and NoSQL optimized for compute. So you can store relational data in a NoSQL database. You just have to do more work. Now, databases do not scale nicely. That is why there's so much benefit to transition to newer age databases like DynamoDB and Aurora serverless. So looking at the example, it's very easy. I have a simple data model, so DynamoDB is great for this. Let's look at how you can compute on the data. I consulted for a new company with a new project. At the kickoff, the development vendor said, we're going to do Lambda for everything, maybe some advanced stuff with containers. And I thought, great, I just came off from a serverless project, we can do this, easy. But the next day at stand-up, they were all talking about containers for the simplest business function. I reminded them it was a fixed price project and there was no time to switch later to Lambdas. The team was not experienced at all with automatic testing, and they struggled so hard adopting Lambdas because of it. They needed to run it locally and manually test. So when you're picking compute, you have to take into account the team. It should fit into your team's skill level. Can they build infrastructure well? Can they do automatic testing? For example, EC2 is much easier to wrap your head around than Lambda. Now, there are several types of tools with different flavors. We have to pick the right tool for the job. Some are appropriate for low latency, others are perfect for scaling quickly. Others are nice for batch processing. The tool you pick should ultimately align with your business goal. So the project goal, what's the short-term goal? Are we finding product market fit? Are we scaling up our product? Or are we improving and iterating? Pick the tool that allows the team to execute on the business goals. So in this example, the team is not very proficient in automatic testing. They understand containers, so we pick ECS. Now we're doing computations, and people are interested in it. Let's look at how we can share these events. One enterprise I helped with really struggled with becoming data-driven. They used SNS to exchange data to each other. There was no supervision though, so it was more point-to-point data exchange. They did not introduce an event bus at the right time. So the biggest problem in events is if you have a wild growth of events. Teams all start building events without a long-term design. Anytime some team needs data, they create a custom event. So this results in point-to-point data exchanges. The data cannot be fanned out to more teams. So the major benefit of decoupling development and integration get lost. And the problem cannot be solved easily, because all teams start to introduce their own data formats. These are incompatible with each other, and they also often have backwards compatibility issues. So, we have two teams. We want to share data. We add an event bridge in every account that can share data between both event bridges. Now it's time to look at how we're going to deploy it to the cloud. I've been in any type of shop. One-man command line deploys to full automated CI/CD multiple times a day. The same principles apply for good CI/CD for a one-man pipeline as multiple teams. You want to reduce the manual work, but sometimes you still have it. What's very important is that you minimize this and make it very functional, so you can deploy it again and again and again. Secondly, you should prefer to separate your pipelines into a build part where this is triggered on every code commit. You include all quality steps here. They produce an artifact and upload them with a version. Then, deploy pipeline picks up the artifact and deploys it to the cloud. It takes a version number and deploys this version. You now have a rollback pipeline out of the box. If I look at the example again, I can use code pipeline to deploy my code. It uses code deploy to actually update the ECS services. Now we want to know, are our systems working properly? And if not, what is happening? One of the often cited reasons CTOs come to me, they ask, I'm not sure if my servers are working properly. Can you help me with this? You can add detailed logging to make sure this happens. The first step is to observe and alert based upon customer experience. We want to know what is happening to the customer. API Gateway is great for this, as it pushes detailed CloudWatch metrics. AWS Load Balancer has less detailed, but at least shows if something is wrong. Now, when there's something is wrong, we want to divide these errors in alarms or tickets. Alarms should be responded upon within a certain time objective. Tickets should be looked at the next working day. The easiest way to do this is to create two SNS topics, one to route alarms to send an SMS, and the second to send a Slack message. The most important thing to do operations well is to have structured log. Every code should have the same, should log in the same way. You should include trace ID to see the business event across all systems, a customer ID so you can correlate with customer support questions, and a business event, what is happening, the steps taken to complete that business event, and either the result or the error. If you have this decent high log hygiene, you can get very high cardinal events. CloudWatch is perfectly fine for this, and CloudWatch Search is really amazing. So, if I go back to the example, I now add CloudWatch for my logging and metrics, and X-ray to do tracing. We still need everything to be secure. Every endpoint gets hit by attack all the time. A DDoS is always around the corner. We also need to analyze for any vulnerabilities. At this stage, we're looking to add frosting on top. We pick specific tooling to build upon extra security that have very specific security goals. Up until this point, we should build everything with security in mind, but it's still good to do a full review of your design. So first, we're going to look at what we're exposing. Endpoints can be hit by DDoS attacks or web exploits. Nowadays, there are no more reasons to use Bastion service in your AWS. You can use AWS System Manager or RDS Data API. Then you want to add security detection, so if something happens, you can react to it. There are a lot of AWS services for this. AWS Guard Duty to detect malicious account level activity, Amazon Inspector to inspect for vulnerabilities, and AWS Macy to detect sensitive data. Now, these actually need to be skipped. So if I now have the example again, I'm going to add guard duty for my account level activity, AWS Macy to detect my sensitive data, and Amazon AWS Inspector to check the vulnerabilities I have. But I also have an endpoint, and I want to protect that. So I add AWS Shield and AWS WAF to protect it. Now we're at the final step, running it at minimal cost. One company asked me for help with the infrastructure cost. They never optimized for this. So I said, sure, let's look at it. And I started with the first team. With a combination of saving plans and scaling down some resources, I saved 20,000 euros a year. This was only 2 days for me. So that's a very nice return of investment. And there were still 10 teams left to do. You should understand how you're built. Everything in AWS is built. So you have to pay for it. The estimated billing should be part of your design. At a restaurant, you get up before you order if you know the cost is going to be too high. And the same should be for your designs. If it's going to be too costly for the company, don't build it. If you have built it, add visibility to it. So set up budget alerts when you're overrunning. Add cost explorer so you can explore where your costs are, and then you can drive down your cost. But the most important thing is to put it in your timeline. The company I told the story about didn't do it. So after your infrastructure project is done, do cost optimization. There's always something that you can optimize. And when you do it, time cap your time for the cost optimization that you're achieving. If you're spending an hour and you're not finding anything, then maybe there's not there. So this is how you can build it in 12 steps. Now I'm going to show you a live demo. The demo illustrates how easy it is to deploy the science of AWS using Java. The code is written using Java Corretto with AWS CDK. The goal is to convey how easy it is to use CDK, and it doesn't necessarily follow the 12 steps that I just showed you. So I'm just going to switch the monitor. So here is my example JFall deployment. It's a very simple static main that uses AWS CDK. Here I give the environment of the account and the region that I want to deploy in. And I deployed this demo app, which could be a library. This demo app consists of 7 stacks, I think. Let me, 1, 2, 3, 4, 5, 6, 7. Yeah, 7. The first 2 are very easy. This one deploys a certificate in AWS Certificate Manager. The second one deploys a container registry. I'm not going to show these because they're very simple and take some time. This one is the VPC. This deploys a full VPC into my account. And it's only about 15 lines of code. First, I set up my VPC. I give the IP address range. I set up DNS support. And I tell it to use 3 AZs. So here I'm already fault tolerant to data center failure. This line creates the VPC. Now I also want to add an ECS cluster. Here I input the VPC and it builds a full cluster for me. Unfortunately, I cannot do a live demo. This would be, the reason for it is that it would take 4 minutes. At the bottom you can see it takes 4 minutes to deploy this. So, how do I do it? I enter CDK deploy VPC, which is available, you can see at the top. There it starts to synthesize your infrastructure. It calculates which asset needs to be deployed, and it will start deploying this. So this takes 4 minutes, so that's why I cannot demo it live. So let's look at the next step. The next step is to deploy a database. This is a single line of code, but I'm actually doing more. And what this shows is the abstraction level that you can achieve using AWS CDK. What we use here is a standardized table. This is a custom class that I built myself, because I want to have some properties on all my DynamoDB tables. As you can see, it extends the table. Now, it sets some defaults. I always want the partition key and the sort key to be PK-SK. This is a best practice, so you can apply single table design later on. Finally, I want to make sure all my data is always encrypted. So I add an encryption parameter here. This one is very easy to deploy. You do CDK deploy data, and it only takes 40 seconds. That's because it's DynamoDB. So let's go back to the demo app. And wait, I need to go back. Here something more interesting is happening. I'm actually inputting to the stack the cluster, the backend repository, and the table. Because this stack needs to know in which VPC cluster to deploy, what ECS container repository to use, and which table to connect to. So I can just use it as parameters. Here you can see the cluster. I make a task definition and give it 4 GB of memory. Then I add a container to the task definition. This is where I retrieve the repository image from the repository that I made in the previous stack. I also add an environment mapping. So when this container comes up, it can use db name to retrieve the name of the table it should use. Then finally, I say I need to add 2 machines for this, because I want it to run highly available. Now something interesting is happening, because CDK recognizes these requirements. The dependency of the data stack, the deployment stack, and the VPC. You can see that in the top half. It will also start deploying this to make sure it's up to date. After that, it will continue on to the other stacks, and then finally, it will also update the load balancer, which I will show in the next code demo. But here you get a prompt, because now you're opening up your AWS accounts to outside traffic. So it asks you, do you want to open port 443 to everyone? The same with the backend. We want to allow different permissions to other resources outside the stack. So here you get a prompt, do you really want to add these permissions? So this makes CDK very easy. Because the final line, I can easily grant access using IAM to the ECS cluster with table.grant read write, and now it can read write data into the table. So this is really cool. Then finally, the load balancer stack. It's very small. Only, again, 15 lines of code almost. It creates a load balancer. It adds a port listener to 443. You add the certificate, and you add the target of the backend. So this is very easy to build. But I already deployed it with the backend. So there's now only one stack left. I retrieve the hosted zone, liveconferencedemo.com. I add a record, jval.liveconferencedemo.com, and I target it to the load balancer. So this is very easy to build your AWS architecture. So to conclude, divide up your AWS architecture into these 12 steps. I'm also running a workshop on this if you want to get a deep dive into it with hands-on experience in infrastructure as code. So it's going to be the 21st of December if you're interested. The key takeaways. You should carefully plan your AWS design and use timelines. What you should remember the month after this presentation is that you should plan your AWS design. And then finally, the key takeaway for a year after this presentation is hopefully plan any big project and use timelines. So thank you for attending my talk. If you have any questions, come and talk to me afterwards. Thank you.